Welcome to This Explainer. Today, we're stepping right into the middle of a high-stakes detective story. But the crime scene we're looking at isn't some dark, rainy alleyway. It's a massive industrial smokestack. And our suspects? Well, they're entirely invisible. We are hunting for volatile organic compounds, or gaseous organic emissions, that are slipping into our atmosphere from industrial sources. To actually catch them, investigators need an airtight, scientific approach to gather irrefutable evidence. Okay, let's dive right into this. How exactly do you catch invisible pollutants before they escape and disperse into the air we breathe? I mean, you obviously can't just throw a giant net over them, right? You need incredibly precise instruments, rigorous field protocols, and, as we'll see, some pretty complex mathematics.
And that brings us to our ultimate forensic rulebook, EPA Method 18. Officially, it's titled The Measurement of Gaseous Organic Compound Emissions by Gas Chromatography. Basically, this is the definitive go-to manual used by environmental testers to capture, identify, and quantify these elusive gases. It's a highly technical, rigorous process, and it's designed specifically to leave absolutely no room for doubt when we're holding industrial sources accountable.
To understand how this all works, we're going to follow a roadmap with 5 steps. 1. Catching invisible industrial gases. 2. The gas chromatographer. 3. 4 ways to sample. 4. Avoiding analytical traps. And finally, 5. Calculating the final number. Section 1. Catching invisible industrial gases. Targeting emissions. Let's establish exactly what we're hunting. Every good detective needs to know the limits of their tools, and Method 18 is definitely no different. This method is highly specialized. It's designed to measure gaseous organics at parts per million levels, and if you're using certain super-sensitive detectors, it can even track them down to parts per billion. That is just incredibly precise. But it does have its blind spots. It cannot measure polymeric compounds, high molecular weight compounds that might polymerize before you can analyze them, or things with very low vapor pressures at stack conditions. So we really have to know exactly what we are looking for before we start. And on top of that, we have to be extremely careful. This isn't just some quiet, relaxed laboratory exercise. We're talking about real-world danger here. The EPA manual explicitly warns that particular care has to be exercised when it comes to safety. Testers out in the field are often working around highly flammable gases, open flames, and potentially explosive atmospheres. Making a mistake out here doesn't just ruin your data, it literally puts lives at risk.
Section 2. The gas chromatographer. Analyzing the evidence. Assuming we safely navigate the industrial site, we now transition from the field into the lab.
Enter the gas chromatographer, or the GC. You can think of the GC as our ultimate interrogation room. See, when testers pull a sample from a roaring smokestack, it's just this chaotic, mixed-up crowd of different gases. The GC forces that entire crowd into a specialized column, separating them all out. Each chemical suspect takes a very specific, measurable amount of time to travel through the system, which the method calls its retention time. By measuring these retention times against known standards, the GC forces every single invisible gas to step into the light and identify itself.
Section 3. 4 ways to sample. Capturing the gas. Of course, before we can interrogate the gases, we actually have to capture them.
Now, what's really fascinating here is that Method 18 doesn't just give you one single way to catch a suspect. It actually gives you 4 specific tactical options depending on the conditions you're facing. You've got integrated bag sampling, direct interface sampling, dilution interface, and the absorption tube procedure. The tester has to carefully choose the right trap for their specific environment and the specific target compound they're after. To give you a real idea of the plumbing involved, take a look at this schematic. This is a single-stage calibration gas dilution system. Sometimes the gas coming right out of the stack is just way too concentrated to be measured directly. So this system uses a component gas, a diluent gas, precise flow control valves, and a T-connector to carefully dilute the target gas. Often, they capture it in a specially made Tedlar bag, so testers can handle the evidence safely without totally ruining it. And that builds into an even more complex setup, the 2-stage dilution apparatus. When testers are dealing with extremely high concentrations of organic materials, a single dilution just isn't going to cut it. In this setup, the system actually separates the highly concentrated waste out through a needle valve, siphoning off only a carefully diluted, low-concentration gas stream. This is absolutely crucial, because it ensures that when the sample finally hits the gas chromatograph, your sensitive detector doesn't get completely overwhelmed and saturated. Section 4. Avoiding analytical traps. Quality control checks. So we've gathered our sample, but the investigation isn't over yet. Think about it like this. Any good defense lawyer, or in this case, a heavily penalized industrial plant, will immediately try to claim that your evidence was corrupted. So testers must proactively prove that their own equipment didn't sabotage the investigation. Method 18 mandates a really strict protocol of quality control measures, specifically known as recovery studies.
Whether you used interface sampling, a bag, or a tube, you must run a recovery study to prove beyond a shadow of a doubt that there were no significant leaks, no cross-contamination, and that the proper procedures were perfectly followed.
Let's look a little closer at how rigorous the bag sampling recovery study actually is. To prove the bag itself didn't somehow absorb or leak the chemical suspects, testers take a sample bag and spike it with a known exact quantity of a pollutant mixture. They aim for a target concentration that's right around 40 to 60% of the average they measured in the field. Then, they store this spiked bag for the exact same time period as the real field samples. Finally, they analyze it. The resulting recovery fraction, what we call the R value, must be strictly between 0.70 and 1.30. If it falls outside that range, the evidence is completely thrown out, and they literally have to start over with a new technique.
Section 5. Calculating the final number. Hard mathematical proof. Once the quality control checks out, we're in the home stretch. So the crucial point here is this. Calculating the recovery efficiency, that R value we just talked about, is essentially the armor that protects the final data. It mathematically proves that your equipment didn't accidentally eat, dilute, or leak the sample. Because of this single step, industrial plants simply cannot wave away the results by claiming the testing apparatus was faulty. And here is exactly how they calculate that armor. Equation 18-6 determines the average fraction recovered, or R. It takes the measured concentration of the spiked sample, subtracts the unspiked average concentration, and divides it all by the theoretical concentration of the spike. It's a relatively simple but incredibly powerful way to mathematically verify the integrity of the whole capture method.
But they don't just file that valid R value away in a drawer somewhere. They use equation 18-7 to actually correct the final field measurements. They divide the measured concentration by that exact R value. This is brilliant because it ensures that the final reported parts per million number compensates for any slight equipment absorption, guaranteeing that these industrial sources are held to exact, undeniable accuracy.
And this brilliantly illustrates the final lockdown of our evidence. Equation 18-1 is one of the primary formulas used to calculate the final concentration of the organic gas mixture in parts per million. By factoring in the flow rates of the calibration gas and the diluent gas, the investigators arrive at the final, indisputable number. That's the number that's going on the official regulatory report.
So, why does all this complex plumbing, this interrogation of gases, and this rigorous math actually matter to you and me? Well, because it holds industrial plants strictly accountable. Method 18 removes that fuzzy margin of error in regulatory reporting. It takes emissions that are entirely invisible to the naked eye and turns them into hard, actionable data. Data that directly protects the air we all breathe.
Which leaves us with a pretty fascinating thought to end on. EPA Method 18 shows us that human ingenuity has created forensic tools capable of measuring the invisible down to the exact parts per million, or even billion. It really makes you wonder, with technology this incredibly precise, what else hovering in the air around us right now is just waiting to be found? Thank you so much for joining me for this explainer. I hope it helps you see our invisible environment in a whole new light.